Our dynamic universe. The key areas covered will be terminal velocity, velocity time graph of a falling object when air resistance is taken into account, including the effect of changing the surface area of the falling object. What we will do today is revise what is meant by terminal velocity and draw a velocity time graph for a parachutist jumping from a plane until they reach the ground. Parachute jumps. We'll be looking at this graph in more depth in a few minutes, but if you want to see an animation with some explanations, you can follow this link. Terminal velocity. When an object falls towards Earth, it has two vertical forces acting on it. It has weight acting downwards towards the Earth and air resistance acting in the opposite direction. As the object falls towards Earth, its velocity increases due to the acceleration of gravity. And when the speed of an object increases, so does the air resistance acting against it. Eventually, these two forces will balance out and the object will no longer accelerate. Balanced forces is equal to a constant velocity, remember. This constant velocity is known as terminal velocity. Here we've got a little graph of terminal velocity. Our graph is velocity against time, and we can see we start off at a zero velocity and it's accelerating, and you can see the acceleration slows down and eventually we reach terminal velocity, which is a constant velocity, so we have a gradient of 0 up at the end of our graph. Parachutes. When doing a parachute jump, the parachute is released to increase the surface area, and as a result, the air resistance or friction increases. This slows the parachutist's velocity, allowing them to land safely. Here is the graph that I briefly mentioned earlier. It's a velocity time graph for a parachutist. I'll explain what's going on in the graph at each point so we can see how the velocity of the parachutist varies with time. Initially, at time 0, the parachutist jumps out of the helicopter or plane. Their velocity starts at 0 and accelerates rapidly. We can see there's a positive gradient there, which is showing an acceleration. This levels out, so their acceleration slows and they reach a terminal velocity. Remember, this is the fastest velocity they can reach. This is where their weight is balanced against their air resistance or friction against them. At approximately 40 seconds, they decide to open the parachute, and this increases the friction or air resistance against them. So the forces are no longer balanced. The friction is much higher than the weight acting on them. This causes a massive deceleration very, very quickly. After the deceleration, they reach a new terminal velocity. So their weight and the air resistance against them is now balanced again, but at a lower velocity because of this extra air resistance. At approximately 70 seconds, this is when the parachutist lands. We can see a decrease in velocity again, but it's a much smaller decrease. That's why they use the parachute. So the smaller decrease in velocity is to prevent any bone breakages or anything awful happening. So we can see the small decrease in velocity is when they're landing. Free fall. Free fall is defined as motion where the only force acting on the object is weight due to gravity. However, we can consider free fall as being the absence of force between two objects both falling at the same time due to gravity, without any external forces, often described as weightlessness. In these examples, we ignore air resistance, or the forces due to friction. Previously, examples using the equations of motion assume free fall. Free fall can also be observed practically in situations where friction does not exist, for example, space. Or on carnival rides. You can follow these two links to have a wee look at some animations showing these.